Welcome to Hot Chips 2024. Session 8, High Performance Processors, Part 3.
Welcome to the last session, High Performance Processor Part 3. I'm the session chair, Lingjie Xu. Today we will have 4 talks in this session. And the first comes from Ampere, Sustainable Computing for AI and Cloud-Native Workloads. And this talk is given by Matthew Erler. Matthew is the processor architect at Ampere Computing. He received his master's in electrical engineering and computer science from Northwestern University, and his BS in engineering from Harvey Mudd College. Throughout his career as an architect, Matthew has been focused on the area of coherency protocols, cache design, on-chip and off-chip interconnects. Let's welcome Matthew.
Good afternoon. My name is Matthew Erler, and I'm a processor architect at Ampere Computing. I've been at Ampere since 2018, where I've worked on developing several generations of processors. Today, I'd like to share with you some technical details about our latest processor, the AmpereOne. But first, I'd like to talk about our company, as this is the first time that we are presenting at Hot Chips. At Ampere Computing, we are focused on developing the next generation of cloud-native processors. So what does this compute environment look like today? Customers are operating at large scales with many users. They want maximum system performance, privacy, and security for independent tasks, and consistent end-user performance. Traditional techniques for improving performance and reducing power are yielding diminishing returns. We can no longer rely on increasing frequency for better performance or process scaling to reduce power. Ampere is driving a paradigm shift where we focus instead on power-optimized designs and scalability to achieve high performance without sacrificing density. A few weeks ago, Ampere publicly announced the AmpereOne family roadmap out to AmpereOne Aurora. While we have many exciting products in our pipeline, today I'll be talking about the first member of the AmpereOne family. As you all know, projects this complex are not the work of one person, but the work of a team. This is a product that hundreds of brilliant engineers have been working on for years, and I'm honored to share the results of their hard work with you today. I want to break the technical discussion down into 2 parts: the Ampere custom core and the AmpereOne SoC. Let's start with the custom core. I'll walk through the main components here, first with the front end, which covers instruction fetch and decode, and then onto execution and the load store unit, followed by memory management, and finally the level 2 cache. And I wanted to show this GDS plot of our chip, this GDS plot of our chip over here, just to kind of give you a sense of what our core actually looks like. And what you can see at the bottom is a large level 2 cache, followed by the other components clustered around each other towards the top. So let's talk about the front end of the AmpereOne processor. The front end is responsible for handling the instructions from branch prediction, instruction cache lookup, decode, to feeding the instructions to the rest of the machine. For branch prediction, we have an 8-table Tage direction predictor coupled with an 8K entry branch target buffer. Our branch target buffer has 2 levels. Level 1 has 256 entries and a 0-cycle latency. Level 2 has 8K entries with a 2-cycle latency. The results are a high branch prediction success rate in the high 90s for our study list. And when you mispredict, we have a very low 10-cycle recovery time. We've implemented a decoupled prediction and fetch pipeline that allows us to continue to predict even in the face of mispredictions or cache misses. We've implemented a 16 kilobyte 4-way L1 instruction cache with a low latency path from our L2 to our front-end pipeline that matches the decode bandwidth to enable streaming from the L2. We've chosen the structure sizes in the front end based on an extensive exploration of a large study list with over 1,000 traces. We sized the structures to deliver the lowest latency for the front end pipeline, delivering to the execution units as quickly as possible. We can decode 5 instructions per cycle or 4 microops per cycle when fusing common instruction pairs. We believe that we have the most aggressive fusing in the industry, allowing for a high throughput from a 4-wide machine. AmpereOne has 8 schedulers feeding 12 execution pipes. We've implemented particularly deep schedulers with 192 total scheduler entries. We have 2 schedulers for memory operations, supporting all addressing modes. Each can schedule 1 load and 1 store per cycle. Our 2 vector and floating point schedulers go to the vector and floating point execution pipes and a shared floating point store data. Both vector pipes support bfloat16 and FP16 as well as AES operations. They also support single microop int8 MMLA. We have 4 integer schedulers that can perform ALU operations, capable of handling 2 branches and 2 complex shifts per cycle. Additionally, 2 schedulers handle multi-cycle complex integer operations such as divides. Next, I'd like to talk about the load store unit in the AmpereOne core. Our L1 data cache is 64 kilobytes, 4-way write through with a 4-cycle load to use latency. Writes are combined in a write combining buffer on the path to the L2. As part of the LSU, we have a very accurate L1 prefetcher, ensuring that data is in the L1 when it's needed. The LSU has been built from the ground up to avoid common vulnerabilities and exploits like meltdown. We have several mechanisms to prevent loads with permissions violations from forwarding data to dependent operations. And we'll talk about this a little bit later, but we've also developed a high-performance memory tagging implementation that's not just a debugging mode, but can be used in production environments. While memory tagging is a system-wide feature with support required in many components, the LSU is a critical part in making sure this is performant. I wanted to spend some time talking about our memory management. One innovation that our core brings is the use of universal TLBs. All entries are universal, allowing any page size to be used for every entry. This approach supports large memory footprint workloads and huge page sizes effectively, unlike implementations with different classes of TLB entries and various page sizes. Our L1 instruction and data TLBs are both 64 entries. The L2 instruction TLB is 768 entries, while the L2 data TLB is 2 times as many entries. We support 8 simultaneous page walks from both instruction and data, which is crucial for large memory footprints where L1 TLBs might be missed. The TLBs have a dedicated interface to the L2 to prevent pollution of the L1 cache during page walks. With a system at our scale of 192 cores, it is necessary to make broadcasting of TLB maintenance operations efficient. We've implemented unique optimizations in our core that allow us to increase the speed of these broadcast operations when appropriate. The AmpereOne core implements a large 2 megabyte, 8-way L2 cache is private per core. This is a key part of our strategy for scalability and consistent performance. Our cache has an 11-cycle load-to-use latency and can schedule a read and a write every cycle. As discussed earlier, the L2 can deliver a full 64-byte cache line to the L1 every cycle. With such a large cache, managing power is important. Put a lot of effort into using the most efficient SRAMs. We've also centralized the control and scheduling logic to reduce power in the data banks. Our L2 can track 48 outstanding requests to the SoC. We have developed several prefetchers, including a best offset prefetcher that we've refined based on internal enhancements and analysis. We have a clever priority-based prefetch queue that we can select so that we can select the most accurate prefetches first. And we'll discuss this a little more later, but the L2 also implements an adaptive throttling mechanism that can change the request rate and traffic profile based on the busyness feedback from the SoC. Now that we've gone through the core microarchitecture, let's start breaking down the SoC. When building our first disaggregated product, our strategy has been to match the subsystem with the best manufacturing process. Compute chiplet, or CCL, is built on TSMC's 5-nanometer process and contains the cores, caches, and coherency engines. You'll see that in the middle in orange. The PCIe and memory controllers each have their own I/O chiplets built on TSMC's 7-nanometer process and consisting of the appropriate controllers and PHYs. Connecting these dies together is an Ampere-developed custom die-to-die interconnect with up to 2.8 terabytes per second aggregate bandwidth in each direction. Our disaggregation approach is designed to enable flexibility and efficiency. Given the modular architecture that we've implemented, we've been able to create a 12-channel platform using the same building blocks as our 8-channel platform. You can see our 12-channel platform over here on the right-hand side of the slide and the 8-channel platform on the left-hand side. This approach allows us to rapidly integrate customer IP, tailoring our I/O to different applications and customers. Here we see the AmpereOne compute chiplet. Let's talk about the major components. We have the core cluster, which is this green block here, which is a group of 4 Ampere custom cores. This cluster is repeated and arranged in columns, 6 columns with 8 clusters each, for a total of 192 cores. On the top right, I've highlighted a block with 2 coherency engines. Here. Each engine contains the system-level cache and snoop filter. This block is also repeated and arranged in columns for a total of 64 megabytes of system-level cache and snoop filters that track 384 megabytes of L2. You can see the repeating structure of the coherency engines kind of coming up and down these 4 columns that have a slightly different shade than the rest of the die. On the bottom right, you can see the die-to-die interface that's used to connect to our I/O dies. And the die-to-die interface similarly repeats up and down on the east and west sides of our compute die. All of these components are linked with a fully connected 8x9 mesh, providing up to 5.7 terabytes per second of cross-sectional bandwidth. Compute chiplet is connected to the MCU and PCIe I/O dies. Each MCU die supports 2 channels of DDR5, with 4 dies providing 8 channels of DDR5 for our initial AmpereOne configuration. The PCIe die provides 32 lanes of PCIe 5.0. Each chiplet has 8 controllers to support different levels of bifurcation. In total, AmpereOne supports 128 lanes of PCIe 5.0. I wanted to shift gears and talk a little about a new feature that AmpereOne is bringing to the data center space. When talking about the load store unit earlier, we mentioned the memory tagging feature. So what is this feature? Memory tagging aims to improve robustness and security. For robustness, memory tagging's ability to detect pointer use after free errors can aid in identifying software errors where pointers go astray, accessing unintended areas. With regards to security, memory tagging can mitigate buffer overflow attacks. How does memory tagging work? At allocation, every memory granule receives an allocation tag. Every time you access it through a pointer, the pointer carries an access tag. The core checks the access tag against the allocation tag for each memory access. If there is a mismatch, a fault occurs, and the data cannot be accessed. The benefits of this capability are apparent when debugging software during development, but it is also useful for cloud applications. In a multi-tenant environment with many different concurrent tasks, memory tagging proves invaluable. AmpereOne's unique implementation of memory tagging allows for a high-performance mode that is precise and efficient. Unlike other implementations, our approach does not use excess bandwidth and memory capacity, allowing this feature to be deployed in a production cloud environment. AmpereOne is currently the only CPU in the data center space that supports memory tagging functionality. And I should mention that this is already available in Linux and some Linux kernels today. In a cloud environment where you have many tasks running concurrently on one processor, it is critical that noisy neighbor effects are minimized and performance remains consistent even at high utilization. I wanted to talk about one of the key features that we have implemented that allows us to address this. We've developed a technology within the SoC and the core called adaptive traffic management. Adaptive traffic management works by having downstream agents like memory controllers or coherency engines communicate their busyness to requesters like cores. The cores can respond to this busyness by adjusting the rate and profile of traffic that they generate. We've built this intelligence into the core to respond dynamically based on their activity. For example, a core running a latency-sensitive application will respond differently than a core running a bandwidth-hungry workload. For an example of how this works, you can see a loaded latency graph of AmpereOne versus a competitor over here on the right-hand side of the slide. In this example, we run a single latency-sensitive application and gradually add bandwidth-hungry applications. As the load on the memory subsystem increases, the latency observed on an AmpereOne processor, shown in red, remains flat and low, while competitive parts in gray show increased latency. Our adaptive traffic management ensures that bandwidth-hungry applications don't interfere with latency-sensitive ones, and the hardware handles this automatically without requiring any software intervention. So we've been talking a lot about how we've built AmpereOne, but what are the end results? These graphs, looking at spec-int rate, show our competitive performance, but also really highlight our power efficiency. You can see our performance here, but the key is really to focus on our power, and thus the performance per watt, which you see up at the top. We've got an exceptional performance per watt. So what does power efficiency do for our customers? In a power and space constrained environment, AmpereOne's better power efficiency allows it to fit more systems per rack, resulting in more performance per rack. You can see this demonstrated on the right-hand side. Here, an AmpereOne processor is able to fully populate a rack because we are not exceeding the power budget of the rack, whereas a competitor system might not be able to fully populate the rack without exceeding the rack's power budget. So our performance per rack is greater. How does AmpereOne fare with more typical cloud-native workloads? In these workloads, you can see our exceptional performance per rack. So again, the numbers that we're sharing here are performance per rack instead of just straight up performance like we were sharing in the earlier slides. We show a couple of different workloads, Nginx, Redis, Memcached, MySQL. And we can see how for these different workloads, Ampere is able to use less rack space by fully populating the racks. In turn, that ends up using less total power and fewer servers. To match the performance of AmpereOne, these competitor systems require more power and more rack space. Now let's talk about how AmpereOne is built for AI. We support a broad range of AI workloads, like natural language processing, computer vision, or generative AI inference. These workloads are typically expressed in these three standard frameworks, PyTorch, TensorFlow, ONNX. We support all of these frameworks out of the box. We do not need a custom conversion or special tools to take advantage of these frameworks. You can use them today. For example, you can use PyTorch to train on an AI GPU and then take the exact same code and run on our CPUs for inference. The message is, AmpereOne is ready to run these AI workloads. It can run them seamlessly with no special handling needed. And while it might be tempting to think of AI in isolation, in reality, AI requires these other domains on the left. You probably want a web application for your large language model. There's often pre-processing of inputs and post-processing of results. Our general purpose CPU is proven to be performant and efficient in these workloads. Here's a sampling of performance on different AI inference workloads. You can see Ampere has excellent performance and leadership in power efficiency. So here we can see the performance on the left-hand side graph. But when we look at performance or inference per watt on the right-hand side, we're exceeding our competitors. Looking at these benchmarks, you can see that AmpereOne supports and excels in a wide array of applications, from web applications to databases and AI and cloud gaming. This list on the bottom of the slide is just a sample of how Ampere has been engaging and contributing to the industry. We are not only building a processor, we are supporting an ecosystem. We have expertise from compilers to operating systems, and we have been working to make sure that the software that's important to you runs smoothly, efficiently, and at high performance. Some of you may be interested in trying AmpereOne out for yourself and seeing how it handles your workload or application. And I have good news. Earlier this month, Oracle announced an OCI Ampere A2 instance. Go ahead and give it a try. And that concludes my presentation. Thank you all for your attention.
Two. Thank you, Matthew. Let's open the floor for questions. Let's start with Slack channel.
So there are a couple of hotspot questions in the Slack channel for you. Let's start with the die-to-die interface. Can you talk about the signaling standard you used or what the pitch of that interface looks like? And let's start there.
Yeah, so I can't really share information about the pitch or the picojoules per bit or the frequency of our die-to-die interface, just because that's not something that we're publicly disclosing at this time. So I'm afraid I probably can't answer the details of that question.
Okay, let's go to the basics. Is there a signaling standard you use, like UCIe or something else, or is it entirely proprietary?
I mean, it's pretty much like a standard die-to-die interface type thing. So it's a high frequency, similar to things like UCIe, but it's not UCIe, just because this is kind of before UCIe was available.
High speed, parallel.
Yes.
Thank you.
Okay, question from floor.
George Kozma from Chips and Cheese. So you have a 16K L1 instruction cache that seems very small. Any insights into why it is that small?
Yeah, I mean, I think that this is something that we spent, quite a bit of time thinking about. So we did an extensive evaluation of our study list to kind of justify the structure sizes of our L1 cache. So one of the things that we were really trying to do was keep the front end pipeline very short. And I mentioned in the slides how we have a 10-cycle mispredict recovery time. And that's very short. And a lot of that is due to the size of our L1. So really what we were trying to do was optimize the latency through the front end to try to get instructions to the execution units as quickly as possible. And that meant spending a lot of effort thinking about how we size our various queues inside the front end. So it was a conscious design choice to make it so we have a low latency so we can get through quickly. And on top of that, you'll notice that we recognize that it's, these kinds of concerns might exist. So we also ensured that our L2 has also a very low latency and has a high bandwidth path into the front end to ensure that we can stream out of the L2 for cases where we are missing our L1.
Thank you.
Go ahead.
Ben Keller, NVIDIA. Can you say anything about the voltage and clocking architecture of your platform?
I'm probably not the expert to be able to answer that question, but I think that if you want to ask that in Slack, that's definitely something that we can try to get an answer to you for.
Okay, thanks.
Go ahead.
Hi, so your design is distinct in being a really large monolithic grid of compute with chiplets around it. So rather than going the mini compute chiplets for core count, you guys want one big block and a big grid. Are you using pretty much industry standard dimensional order routing on the mesh on die? And if so, what's your longer term plan for dealing with asymmetries and hot spotting for columns and rows going into and out of the memory and PCIe interfaces?
So we definitely have done a lot of studying on kind of how to manage hot spotting. And so, yes, we are roughly speaking dimension ordered on our mesh, but there are abilities to change that in certain cases to avoid hotspots. I don't want to be specific about exactly how we've done it, but it's definitely a complexity of all meshes, and particularly when we talk about disaggregation, is how do we handle, typically you aren't going to be able to have, links for every column or row in your mesh. So that's definitely something that we're aware of, and we've put a lot of work in. I can't talk about future products and how we're addressing that, but it's definitely something we're aware of and are working on.
Oh, thank you very much.
Let's see if we have more questions from Slack.
Okay, your concept of memory tagging produced a lot of questions. Do you store the memory tags in your memory? Do you need extra capacity for that? Does it affect the bandwidth?
So I did mention it, those two questions specifically.
They want more detail.
I'm sure. So it does not impact capacity or bandwidth. So I don't want to go into the details of the clever tricks that we've played, but they're definitely, we're not trivial, and I'd say it's one of the real innovations of this product is our ability to offer memory tagging that is performant. So this is not just something that you would be using for debugging your code. This is something that you can actually use in a production environment. And I think that's really important.
That's why it spawned all the questions.
Yeah, so exactly how we're doing that, I'm not sure I can answer that question.
Okay, there's a related one. Maybe you can answer this one. With 4 bits of memory tagging, you can only have so many in flight. When do you decide how to rotate or reuse the tags? Or is that also?
I'm not sure that I can answer that question really well, but take it to Slack, and we'll work on answering that question.
It's in Slack already. Okay.
Okay, I'll respond in Slack.
One last quick question from the floor.
All right, Joe Byrne with XP.pub. You showed a picture of the compute die.
Yeah.
Just wondering, maybe I missed it. How big is that die in square millimeters?
I don't think we shared it. I know that there's some pictures online of our package, and then there's probably somebody out there who's going to take some measurements of the package and figure out the size of the compute die, but I don't actually know it off the top of my head. But it's big.
Well, can I ask a memory tagging question? So ARM has memory tagging extensions. Are you not compliant with the ARM standard MTE?
We are. So that's when I mentioned that this is really part of the Linux kernel. So we're not the only, memory tagging is an ARM thing, but it does not exist in the data center and any of the other ARM instances that we're aware of, and obviously wouldn't exist elsewhere because it's part of the ARM ecosystem. So we're compliant, but we're also the first implementers, and as I said, we're high performant.
Okay, thank you.
Okay, this is the end of the first talk. Thank you, Matthew. We'll begin the second talk, Inside Maia 100 from Microsoft. We have 2 speakers for this session. First speaker is Sherry Xu. Sherry Xu is a partner architect at Microsoft, where she is leading the Maia silicon architecture team. She has joined Microsoft for about 10 years and has worked as a silicon architect for various projects, including Xbox. She has over 20 years of experience in silicon architecture and development. And the second speaker is Chandru Ramakrishnan. He is a partner software engineering manager at Microsoft, where he leads the team responsible for the Maia 100 runtime and kernel library. With over 2 decades of experience in software engineering and management, Chandru has worked on large-scale distributed systems and services at both Microsoft and various startups. Let's welcome.
Good afternoon. So today, Chandru and I will give an overview for Maia 100. I will cover the SoC architecture section, and Chandru will cover the software section. So this is a chip conference, but everyone knows how important is software. And we will show how the software help us to improve performance per watt. And also, Chandru will give an example how we map the kernel to the hardware. So since last November, Microsoft announced its first generation custom AI accelerator. This Maia 100 is target large-scale AI workload, and it developed specially for Azure to run production open AI model. Through vertical integration, we try to optimize performance and reduce cost. We've done this through software-hardware co-design to unlock new capabilities. We also have the custom-built server board with a tailor-made rack. By doing all this, we try to improve power efficiency. The first generation Maia 100 designed for wide deployability. So Chandru will share the software stack we built for Maia 100. Maia 100 is also built with the assumption of liquid cooling for the cooling solution. And through the Maia 100, we enable liquid cooling, which can also be used for other Azure programs. This is a high-level spec for Maia 100. So Maia 100 is a reticle size SoC using TSMC M5 technology. For interposer, we choose to use CoWoS-S, and inside the package, we have 4 HBM2E stack Total give you a 1.8 terabyte per second bandwidth and 64 gigabyte HBM capacity. To enable to run large-scale AI model, we have provisioned 600 gigabyte full duplex Ethernet bandwidth. The peak throughput for the Maia 100 can reach 3 petaops for 6-bit data type, 1.5 petaops for the 9-bit data type. BF16, we can offer 800 teraops. One special thing for Maia 100 is it has a large L1 and L2 scratch pad, total about 500 megabytes in the SoC. For host interface, we have a Gen 5x8 PCIe interface. Maia 100 is designed to support up to 700 watt TDP. Now, in data center, when we run our target workload, for the inference workload, we find 500 watt will give you the best performance per watt. So Maia 100 is using provision power of 500 watts. This is a Maia 100 block diagram. So on the right, we show the basic building block, which is tile. Tile consists of a tensor unit, a vector engine, a tile DMA engine to move the data, and a tile control processor. On top of that, there's a L1's SRAM, which the TDMA will use to move data between the L1 to the L2. Inside the cluster, which is the next level of hierarchy, there's 4 tiles. On top, we provide a cluster-level data movement engine and a cluster-level control processor, along with a large L2 SRAM. There's a total of 16 clusters inside the SoC. To support confidential compute, we also have security engine built into the SoC. And to enable image-based workload, we have a couple image decoder built into the SoC. Let's look at a couple of ML-specific features for Maia 100. Maia 100 has a high-speed tensor unit. This tensor unit supports a wide range of data type. So some of the data type, including 9-bit and 6-bit. We have experimented multiple data types during the development time. And those data types used in Maia 100 later evolved into the MX data type, which Microsoft started driving the MX consortium since last year. The tensor unit is constructed as a 16 by R by 16 unit. We choose this size as a trade-off between granularity loss and the peak performance. Maia 100 has a vector engine with custom ISA tailored for machine learning. It's a loosely coupled superscale engine, support data type including FP32 and BF16. We have multiple DMA engines in the SoC, support different tensor sharding. This can improve the data movement efficiency. Maia 100 is using asynchronous programming model, and we have a hardware semaphore built to support this asynchronous programming model. Now, data movement is a well-known bottleneck for inference workload. So Maia 100, we have a narrow data type and also data compression to help improve the storage and the data movement. In addition to the 6-bit and 9-bit data type, we also have a 4-bit storage data type. We have L1 and L2, which is purely software managed. With the large size of L1 and L2, we can increase the data reusability, which will reduce the power for HBM access. Maia choose to use a mesh-like NOC topology, which also has a specific machine learning feature built in. Microsoft has led the Ultra Ethernet Consortium and tried to enable the Ethernet-based interconnect for high-speed compute. So for Maia 100, we choose to use the Ethernet-based backend network with built-in encryption engine to help protect user data. For each Maia 100, we provide a all-gather and a scatter-reduced bandwidth up to 4,800 gigabit per second. Any-to-any bandwidth, we can support up to 1,200 gigabit per second. We use a customer Rocky-like protocol with enhanced reliability and load balance feature. The AES GCM engine is built in to support confidential compute. Maia 100 choose to use a unified network, so we can support both direct and switch connectivity. This creates a lot of flexibility, so same network is used for both scale out and scale up. On the right, you see a picture of how Maia 100 is connected with multiple devices together. Now, I pass the talk to Chandru to talk about our software stack.
Thanks, Sherry. Hi, everyone. So I'm going to dig a bit into the software stack for Maia. And I'm going to introduce the Maia SDK. The goal of the Maia SDK is really to make easy porting of models written in Triton or PyTorch to Maia. And we have a number of components which enable that. The first is we built a PyTorch backend for Maia, and that supports both eager mode and graph mode. We have a set of developer tools, debuggers, profilers, and validation tools, which allow you to debug and profile and performance optimize models on Maia. And then we have compilers. We support 2 programming models for Maia, Triton and Maia API. I have a slide which is going to go into details for that, and then we have compilers for both of them. Using these compilers, we have built a really high-performance kernel library, which composes of compute and collective kernels, and this allows you to get quickly started on Maia. We also support custom kernels if you need them there. And the bottommost layer is the Maia host device runtime and the hardware abstraction layer, and it's used for things like memory management, kernel launches, scheduling, as well as device management. So as Sherry said, the Maia programming model is an asynchronous programming model which uses semaphores for synchronization. On this picture, on the left-hand side, you have control processors, the cluster control processor and the tile control processor. And they feed asynchronous commands into the copy engines, the network connections, the tensor unit, and the vector processor. The structure of a command is it takes a set of input semaphores, a set of arguments, and a set of output semaphores. It waits for the input semaphores to signify that the input data is ready and the output buffer is available. It executes the command, and it signals the output semaphores. So basically, the synchronization happens on the data path here. So as I said, we have 2 Maia kernel programming models. We have Triton, which is an open source DSL for deep neural networks. This is the portable option where you can write the same Triton program for GPU and execute it on Maia. And then we built a Triton compiler, which takes Triton source and lowers it to Maia API. Maia API is a lower level programming model which allows you to finally control everything. Just to compare these 2 programming models, flash attention is hundreds of lines of code in Triton, whereas in Maia API, it is thousands of lines of code. Triton is hardware agnostic. Maia API is Maia specific. In Triton, you write a single program. It runs at the Maia cluster level. And on Maia API, you're actually writing 3 programs, 1 for the cluster, 1 for the tile, and 1 for the vector processor. In Triton, the compiler takes care of semaphores, memory management, double buffering. In Maia API, it's the programmer's responsibility to do all of that. So next, we're going to walk through running a large-scale distributed gem on Maia and what we have done to optimize that. And we've used a gather-based approach here as opposed to a traditional all-reduce-based approach. The reason we have done this is it allows us to fuse the activation function like ReLU into the gem. We can overlap compute with network communication, And then it allows us to send quantized data over the network. On the left, if you see, we have an example of multiplying activation matrix X with a weight matrix W. This gem is going to run across 4 Maia devices, and the X matrix is M by K, and the W matrix is K by N here. So the first thing we do is shard both the X matrix and the W matrix by columns. So each Maia device contains a K by 4 shard of the X matrix, and it contains an N by 4 shard of the weights matrix. On the right, we have a detailed execution flow of what happens on a single Maia device. We execute the gem in 4 phases. In the first phase, we use the tensor unit to multiply the first shard of X with the first shard of W to get our intermediate result Y. While that's happening, the ANC is doing a network transfer of the next shard of X, the second shard of X. This is an example of how we overlap compute with network communication. Also, the activations can be sent quantized over the network with this model. So we proceed to phase 2. In phase 2, we multiply the second shard of X with the second shard of W to get our second intermediate result. And then, we are in parallel, we're retrieving the third shard of X. And in phase 2, we can use the vector processor to kind of sum the 2 intermediate results there. So we repeat for phase 3 and 4, and that's how we get our final result. So this is a highly optimized on-chip flow. Weights are always loaded from local HBM. We further partition the computation across clusters, and we use the NOC to do an on-chip activation gather. We also heavily leverage SRAM in this flow, both to buffer activations and for intermediate results, as well as to reduce HBM accesses for network traffic. The picture on the right shows that we have the ability to do a network read and write directly from CSRAM, so we don't have to go through HBM for that. So our PyTorch integration, our goal of a PyTorch integration is to run a model with a single line change. For that, we've developed a PyTorch backend which supports both eager mode and graph mode. We also have a high performance kernel library which supports a set of PyTorch operators which are used in popular large language models and small language models. For graph mode, we have integrated directly with the torch.compile ecosystem. And here's an example. This is the Mistral model. You can get it from Hugging Face. And to run it on the Maia device, you just make 2 changes. You import Maia backend, and you change the device to Maia. For models that span more than 1 device, we have a communication library. It's called Mickle. We've integrated this fully as a Torch distributed backend, and we support all the operators that PyTorch supports. And lastly, we have developer tools. And the developer tools allow you to code, debug, and profile using the Maia SDK. We have Maia SMI, which is a device management tool. We have a Maia debugger, which supports both a command line experience like GDB, as well as a VS Code plugin. So it's an integrated IDE experience. We have a crash dump analyzer, which can show you fault details as well as analyze call stacks. We have a fully functional virtual platform called Maia Sim, and this allows you to develop locally on Maia. You can even develop on your laptop. As we covered, Maia is an asynchronous programming model. So this leads to this can lead to subtle race conditions and bugs. To help with that, we have a race condition analyzer as well as an execution graph analyzer. We have a logging and profiling library which helps you instrument code. And then we have Maia Profiler which allows you to analyze traces and performance optimize kernels. And lastly, we have MaiaMon, which is a monitoring and resource usage and monitoring tool there. And that concludes our presentations. So we can transition to questions.
Okay, before we open the floor for questions, I actually have a burning question.
Yeah.
So you guys said the first generation of Maia is targeted for inferencing, but the spec is pretty powerful. Does Maia 100 train models internally?
So we design for both inference and training. That's why you see it's pretty powerful. Currently, we are running inference workload.
Currently, we're focused on inferencing using the Azure OpenAI service.
It does have the potential to train the models, right?
Sorry?
It does have the potential to train.
Yeah, it does. It does, yeah.
Okay, all right. All right. Questions from the Slack, please.
Okay, and that was one of the questions from Slack right there, so you got it covered. This one comes from someone at Gray Research. To what extent is the Maia architecture informed by the design of the brainwave NPU? That was covered back at Hot Chips in 2017.
Yeah, so Microsoft has worked on custom silicon for a long time, right? Back to Xbox time. We do leverage quite a from the past program, including brainwave. And you can see the data type is along the study and the leverage we took from brainwave.
So that would be the 6-9-bit.
We are continue working on the data type. So there's a lot of study, a lot of research. We end up pick this for Maia 100.
Thank you.
Okay, questions?
Thank you for this presentation. This presentation was in the style where it was a lot of what you guys did, but there was very little, at least I heard little about why. So I was wondering if you could comment a bit on, obviously as Microsoft, you have lots of options. You could, there's a lot of AI accelerator startups. And then, so I was wondering if you could talk about what was the scratch that you were itching? What was the thing that you found lacking in, for example, NVIDIA GPUs that motivated you to make this, and as well, if you could, why, and then what are the key architecture differences in terms of just conceptually, philosophically, between the NVIDIA GPUs and Maia's approach?
Maia 100, the reason we do it is really try to enable vertical integration, right? Software, hardware co-design, make hardware simple, but take advantage of software to get more power efficiency. That's one of the reasons we try to do this program, right? I'm not going to compare ourselves with NVIDIA, but we listed the feature we think are special for our chip. For example, we have very large SRAM, we have very high throughput tensor unit. We don't use cache, we use scratchpad, right? And we also have provision very high bandwidth backend network to enable scale out. So I would not like to compare with NVIDIA, but this is the things that Maia is designed specially for the machine learning workload.
Thank you.
Okay, next question.
George Kozma from Chips and Cheese. So what exactly are the data formats for the 4, 6, 9-bit data formats? So what's the mantissa and exponent?
I don't think we are ready to share this publicly. As I said earlier, this is a data type eventually evolve into the OCP consortium, the MXN consortium. So this is an early instance of that work. I don't think we can share the details of that data format publicly at this time.
Thank you. I actually answered a lot. Thank you.
Okay, question from the Slack.
This one comes from someone at Waymo. Can the clusters talk directly to each other, or do they have to use the L2 cache as their communication mechanism?
The cluster can talk. The cluster can talk to each other, yes.
Any more details on how that works?
I don't think we are ready to share more details, but yes, cluster can talk to each other.
Thank you.
Question.
Hi, Ange Bennett, Semi-Analysis. Hi, Sherry. You are using HBM2E, which I believe does not include error correction. So how do you approach the issue of maintaining reliability for inference, which is production on customer loads, I would think?
Yes, so we do have our own error correction scheme implemented to help enhance the reliability, to reduce the reliability impact.
Dedicating some of the capacity to that?
No, I don't think I can share the detail yet. This is one of the concerns, and we have addressed special, we do have a take action to address that.
Thank you.
Do you have more questions from the Slack?
We do indeed. This one comes from Marvell Semiconductors. Earlier, AMD was talking about how everyone's trying to unify behind an open source ROCm. How does that work with the Maia kernels?
Yeah, so we are working on, like I said, for the portability layer, we're focusing on Triton as being the portability layer, and then we have Maia API, which is a low-level programming model there for Maia.
Okay, thank you.
Yeah.
Okay, so last question from me. So will you offer Maia 100 on Azure Cloud? If so, would that be like a TPU, you expose your framework, or it will be like GPU you provide with your bare metal hardware?
Yeah, so we do have Maia clusters live serving OpenAI inferencing of models. Right now it is offered for internal Microsoft use cases there. Yeah.
Okay, thank you very much.
Yeah.
Let's thank Sherry and Chandru for the presentation.
Thank you.
Okay, let's move on to talk number 3 from AMD, next generation Zen 5 core. So we also have 2 speakers for this session. First speaker is Brett Cohen. He is currently the Zen 5 architect and a senior fellow at AMD. Brett joined AMD in 2008 as an RTL designer on Bobcat, the low-power x86 core in AMD's first integrated APU. He led the Cat family RTL team on its second-generation Jaguar core, AMD's first game console core, and then joined the Zen family RTL architecture team at Zen's outset. The second speaker is Mahesh Subramony. He is a senior fellow design engineer at AMD and was the SoC architect for the multiple Ryzen processors, including first-generation Threadripper and the 3000 to 4000 series desktop processors. Since 2003, he has been with AMD in architecture and design on SoCs spanning mobile, desktop, and servers. Let's first welcome Brett.
Thank you for the introduction, and hello. I'm privileged to be here at Hot Chips to share information on AMD's next generation Zen 5 core and its microarchitecture. Mahesh Subramony, as you heard, will also present, but he's going to present information on Zen 5 based client parts. Zen 5 is the latest step along AMD's high-performance x86 CPU roadmap. We've continued the cadence of delivering double-digit power-efficient performance increases and adding key ISA while utilizing state-of-the-art technology. The combined double-digit performance increases in IPC demand a constant stream of innovation. And we open up each of the outcoming cores to that innovation, starting from a blank sheet where needed. Zen 5's high-level objectives started with that performance mandate, but also to lay a new foundation for not only this core, but for future generations. That meant maintaining balance across the microarchitecture required for efficient increases in both performance and throughput. We wanted to grow parallelism and throughput where we could, and that meant some of the familiar back-end and performance improvements, such as more integer and floating point execution parallelism, high throughput, efficient data throughput through our load, store, and cache hierarchy, and implementing a full 512-bit compute and data paths within our FPU. But we also extended parallelism to the front end of the design. The increased parallelism and throughput throughout the design extends and gives a balanced overall performance uplift. Along with the performance objectives here, Zen 5 also includes features to flexibly grow its solution across multiple platforms. There are additional ISA extensions. There's support of configuration of some of the hardware. And there's also support of through Zen 5 and Zen 5C core variants, which provide performance and scalability options. Since I've used the terms front end and back end, I put boxes in the graphics to show the partitioning. When I say front end, I mean starting at branch prediction is all the top part, and really going through the dispatch. And everything post-dispatch is the back end on both the integer and floating point side. I'm going to give you a quick overview of some of the microarchitecture and the flow through the machine before talking more through each of the major units. Some things you keep and you don't change. Now you've heard different other places make different decisions, but Zen 5 continues to support 2 threads per core to deliver maximum 1T performance while enjoying 2T throughput and power performance efficiencies. We've seen that to be the case, and that's a keeper for us. Zen 5 extends capabilities throughout each of the major design blocks as well, with the next generation branch predictor, a more capable, higher throughput cache hierarchy, dual pipe front end, wider dispatch and execution, and also more TLB capacity. We'll see how these combine with the data flow improvements here. If you don't have a balanced design, you constrain overall performance and have wasted opportunity. For Zen 5, we were significantly growing our execution resources and opened up the front end of the design to feed the machine. You'll hear a lot of 2x or doubling throughout the rest of the presentation. And the graphic shows our basic flow paths through both instruction and data fetch, instruction fetch and execution. So flow through the machine starts with branch prediction delivering 2 taken predictions or basic blocks per cycle. The prediction stream flows down through a dual pipe front end and feeds the 8-wide dispatch at the back end of the machine. The integer execution units widen from 4 to 6 ALUs, and our data flow starts with its 4 address generation units or AGUs, which are paired up with our 4 load store pipelines. You can see the arrows over there. The floating point unit increases to 4 execution pipelines, which have a full 512-bit data path and are fed by 2 512-bit loads and can output 1 512-bit store per cycle. We'll look now at more detail on the various units. It all starts with branch prediction, which is a major lever for both performance and efficiency, as it sets the path for our work. Zen 5 is invested to implement an L2-sized L1 BTB, larger cage, and also larger return address structures. And our branch predictor combines these to deliver a 0-bubble conditional branch prediction stream, again with 2 taken predictions per cycle. We aggressively fetch from this prediction stream and translating and initiating the any required iCache accesses. The parallel fetch paths that we have for those can hide L2 latencies to both the TLBs and the iCache, and our larger L2 TLB means that there are fewer table walks required as well. Zen 5's decode unit invests in a denser, more efficient op cache, which has increased associativity and stores instructions or fused instructions rather than ops. And our 2x story continues here. The op cache is accessed via 2 parallel op cache pipes and can output up to 12 instructions per cycle. There are also 2 decode pipes which are fed by the 2 incoming instruction streams. And these fetch decode accesses can happen in parallel with the OC fetches, with the op cache fetches. Sorry, I'm lapsing to my acronyms. And both of these, the fetch decode accesses both feed the UOP queue for the current access, but it also trains the op cache for efficient and performant future accesses. The UOP queue, micro-op queue, aggregates both the decoder and the op cache output to feed Zen's 8-wide dispatch to the back end. Zen 5's integer execution unit takes the 8-wide dispatch through an 8-wide register rename, and it also outputs it in an 8-wide retire rate. in between, the larger unified schedulers feed 6 ALUs and 4 AGUs. The execution window grows with a larger physical address file, and also the reorder buffer, or retire queue, increases to 448 entries. Symmetry throughout the integer execution streamlines instruction pick from our unified ALU and AGU schedulers, and it enables age order picks throughout. Vector throughput. Zen's floating point unit brings a 512-bit data path to each of its 4 execution pipes. FPU-related load store bandwidth increases to 2 512-bit loads and 1 512-bit store per cycle. The additional width per pipe, along with an increase from 3 to 4 execution pipes, and this high-flow data access, drive our vector throughput to new levels. In addition to the throughput increases, there are also latency improvements, such as reducing the floating point add latency from 3 to 2 cycles. The overall execution window expands and combines with the throughput and latency improvements to allow more parallel execution throughout through the resources. Some execution window enhancements are the non-scheduling queue growth to 96 entries, up from 64. We added, as I said, a third scheduler, and also have increased the size of all the schedulers from 32 to 38 entries, so that's a big growth. And we've doubled our vector registers from 192 to 384 512-bit registers. We've talked about performant, efficient throughput, and Zen 5's load store data cache unit is the driver of those back-end data accesses to feed execution. The LSDC unit grows the L1 data cache and its associativity by 50% over Zen 4's cache. And it does this, but yet still maintains its 4-cycle load to use, even with the growth, which is great. There's an additional min pipe, memory operation pipe, over Zen 4 for a total of 4 pipes and those pipes can be filled with either 4 loads or a mix of load and store ops with a maximum of 2 stores per cycle. We've doubled the L2 to L1 bandwidth, and now can also deliver, as I said, the 2 512-bit loads per cycle from L1 to feed AVX, and this is great for boosting HPC and AI workloads. We also tuned our data prefetching algorithms for improved performance and stride pattern recognition. So, we've highlighted some of the key cache hierarchy features already, such as the doubling the L2 and L1 bandwidth for both the instruction and the data cache. But we also have doubled L2 associativity, and we've reduced L3 latency by 3.5 clocks. So in addition to those, I'm going to use this slide to show an extra set of constraints and deliverables that our cache hierarchy team has. And that's really creation of building blocks that can be efficiently assembled in multiple configurations while minimizing latencies across the design. You're aware of AMD's effective use of the chiplet technology to deliver SoC product. And our building block methodology extends through multiple levels of the design, though, from chiplets within a package to core L3 configurations within a core complex. And this is a CCX, or a core complex here. The graphic shows partitioning and high-level floor plan of a typical 8-core CCX, and that forms one of our basic building blocks. Zen 5 also drives a family of implementation points to expand its solution space and within and across market segments, and it gives scalability and performance options. The Zen 5 point establishes our highest performance 1T implementation. And we also have created Zen 5C at a point which is optimized to deliver throughput and avoid performance performance cliffs. But with this implementation, we simultaneously have created another efficient area and power sweet spot. And Mahesh will later show you how this plays out in some of our products and how they leverage this flexibility. Zen 5 also brings a set of instruction set architecture additions. There are AVX extensions and further instruction support for efficient data movement and prefetching. We also bring continued enhancements to AMD's secure encrypted virtualization and enhancements to our general debug support. Over the years, AMD's Zen has driven what it means to be a high-performance, power-efficient x86 processor, and Zen 5 builds on this legacy and the Zen family performance per watt advantages. While we keep and extend fundamentals such as clock and power gating and driving 1T performance while also leveraging 2T efficiencies, we also prioritize some changes which can both boost performance as well as reduce waste and the power required to do that work. A great front-end example is a branch predictor, which directs us through the correct path. And by minimizing mispredicts, you're minimizing work that you have to throw away and burn power on. We also look to eliminate wasteful data accesses, and that's a win for both the individual core as well as other cores in the system, others as a whole. Eliminating memory accesses frees overall system memory bandwidth and directly decreases the individual instructions latencies, while avoiding the power that those additional fetches would cost. And a great example here is with some of the optimized string instructions, which use flexible coherency to avoid making fetches that the same instruction is going to overwrite. Also, the improved prefetching is another great example. Zen 5 had a balanced contribution of performance uplift across the core. I've included a graphic here to give a visual of the relative contributions of the various units. It's SpecInt 2017 AOCC. This balance across the core, again, is critical to having efficient overall uplift. Now, if this large footprint workloads, you'd see the ICBP section grow more. And so it would be a larger percentage of the whole. And there's also a table here that summarizes key microarchitectural advances that I've already talked about in our walkthrough. This chart shows the generational performance comparison of Zen 5 to Zen 4 across a set of client workloads. Zen 5 shows an average of 16% uplift across these workloads. Zen 5 also shows a performance advantage in server applications. Here you see the comparisons of Zen 5-based Turin systems for molecular dynamics and Llama workloads relative to a competitor. With its performance uplift and broad solution space for platform optimization, Zen 5 is the engine for AMD's latest Zen family products. And Mahesh is here now to talk about some of those Zen 5 client-based products.
Thanks, Brad. Yep. Right, so let's take a look at how the Zen 5 core is employed in the client SoCs. I know Brad mentioned this, but I want to go back to the construction of the CCX, or the core complex, as well as the core complex die. The text in yellow indicate the deltas between the prior generation of the Zen 4 core. So starting with the D cache, we go from 32 to 48K, 50% increase. Also a 50% increase in associativity, going from 8-way to 12-way. The L2, the private 1MB L2, again doubles its associativity, going from 8-way to 16-way. The bandwidth is doubled as well, going from 32 bytes per cycle to 64 bytes per cycle. And the DC supports 4 loads and 2 stores per cycle. Again, if the load is a 512-bit operation, that reduces down to 2 loads and 1 store per cycle. So all this increased bandwidth it results in improved throughput and higher instructions per cycle. Now, a finite number of these core plus L2 engines are attached to a last level low latency shared L3. And that L3, like prior generations, is populated almost entirely by evictions from the L2, so it's a victim cache. It also stores L2 tags that are duplicated for probe filtering, especially in SoCs that have large caches and multiple caching agents. So that's the CCX construction, and that construction enables us to create multiple CCXs of varying core and cache sizes that cater to the needs of each of the product types. And we have various product swim lanes that we have to cater to in the client space. Starting right at the top is the Granite Ridge desktop SoC that has two CCDs, or core complex dies, at the heart of which is a 8-core, 16-thread, 32 MB L3 CCX. So with 4 MB of L3 per core, a 512-bit data path for the FP. Two of these CCDs can be featured in a single Granite Ridge SoC for a total of 16 cores and 32 threads, 64 MB of L3. So this homogeneous architecture lends itself well to uncomplicated scheduling, especially for the desktop user that needs every task to perform with low latency and high performance. So the architecture lends itself well there. From a compute standpoint, even though the requirements are not that far off for a client SoC, there is a little more focus on power efficiency. And here is where that second design point of that compact core that Brad talked about comes into play, and we are able to create a heterogeneous architecture for our APU. The Strix Point SoC features two unique CCXs, or core complexes, a 4 classic 16 MB L3 core complex with a 256-bit FP data path. Again, a 4 MB L3 per core, giving you the responsiveness that is so required for that mobile SoCs. And for the performance scale-out, it employs the 8 compact 8 MB L3 CCX. Again, 1 MB L3 per core, really reducing the power footprint of it to give you that performance scale-out without breaking the bank in terms of power efficiency. So having that flexibility of creating smaller, larger CCXs, homogeneous, heterogeneous, allows this Zen 5 CPU to proliferate within AMD's wide portfolio, supporting products ranging from data center to embedded. Let's take a quick peek at the Strix Point SoC. At a first order, it is just increased compute across all the major pillars of compute, if I want to call it that, across CPU, GPU, and NPU, and delivering increased performance, significantly increased performance compared to its predecessor, the Phoenix Point of the 7040 series of processors. From a core standpoint, as we had covered, two unique CCXs combined, they are 12 cores, 24 threads with a 24 MB L3, a 50% increase in core count and L3 compared to the prior generation. Now, architecturally, this is the first time we have a Ryzen processor where we have two CCXs in the same SoC that have asymmetrical core count and asymmetrical L3s. Right? So in all prior Ryzen SoCs, we had homogeneous CCXs. And what that means is that a single core's view of the cache hierarchy multiplied by the number of such containers in the SoC would be enough to perfectly describe the entire cache topography to an OS. Now that changed with this SoC once we introduced asymmetrical L3. So there was design innovations that went in to be able to express this architecture perfectly to the operating system. Now, from an architectural standpoint, while there are certain benchmarks that might not clearly show the advantage that this architecture brings, especially with these benchmarks running in clean room environment, we know the real world is not clean room. There's going to be hero threads and background threads. So in the presence of applications really demand that responsiveness and background threads that are running, having two compartmentalized CCXs where if the processes are scheduled properly, they don't pollute each other's common last level cache, we believe will drive a better user experience. Now, we have improved significantly on the GPU and the NPU as well, which we're going to cover in subsequent slides. Outside of that, there is an array of accelerators and microcontrollers to support all of the functions, including multimedia, security, manageability, and system management. It also features a rich I/O cluster, which includes 8 USB ports, a combination of USB 4, USB 3, and USB 2, 16 lanes of power-efficient Gen 4 PCIe, 128 bits of a combo DDR5 that supports both LP5 and DDR5, right? So all of this compute, all of this features added in meant that this SoC was over 20% larger than the prior generation Phoenix SoC, but the team was still able to squeeze this into the same footprint of the FP8 package infrastructure, or 25 by 40 package infrastructure, which lends itself well to OEMs when they have to design platforms with some backward compatibility. Now, a larger die also meant that the Infinity fabric, both from a data and a control standpoint, grew in size. So innovations were made to ensure that we have sub-component power gating. So if only a portion of the data fabric was going to be used for particular use cases, the entire rest of the fabric can be gated, both clock and power, conserve energy. So innovations, when you grow the die, again, still managing to increase the compute while being power conscious, given that there's a mobile SoC. Clicking forward to the RDNA 3.5, as the name indicates, it's a minor rev click over the RDNA 3 engine. So taking all the goodness from the RDNA 3 engine and then adding a little bit of power efficiency, as this has to be catered for the mobile SoC that it's going into. From an architectural standpoint, it is a larger engine. So it is a single SE or a shader engine, dual SA shader array, 8 WGP or 8 workgroup processors, 4 render backends, or 4 RB pluses with a 2 MB GL2 engine. With a peak frequency of 2.9 gigahertz, it results in over 11 teraflops, which is a 30% improvement over the prior generation. So a bigger engine, but at the same time, enhancements have been put in place to make sure that this larger engine performs in a more power efficient manner. So looking at the texture subsystem, 2x sampler rate, some of the most common texture sampler instructions have gone double rate. That increases the throughput. The point sampling acceleration, so a hardware detects flat sampling, sends those ops down a more power efficient path, again, conserving power. From a shader subsystem standpoint, the rich vector ISA for interpolation and comparison, a good chunk of them are now dual rate, so that does improve performance. There is a floating point unit in the SALU, so any wave computer that needs to run simple floating point now gets a boost in performance. The skip single-use VGPR, right? So there's instructions that always create a data once and is discarded. We have a new ISA that we are able to detect that early and forward the result of that instruction to its subsequent instruction, eliminating a write. Again, performance per bit, better memory management that ultimately leads to better performance per watt. Looking at the raster subsystem, RDNA 3 processes geometry in batches during pixel shading, and that allows us to take advantage of spatial locality, working out of the cache more often and not having to go to memory. RDNA 3.5 takes it a step forward, enables sub-batching, improves that ability to be more efficient. Programmable bin order really exploits temporal locality. So having the capability of programming those bin orders, ensuring the likelihood that the first bins of a new batch are the last bins of the previous batch enables us to ensure there's not a lot of memory thrashing going on. So overall, there's also memory subsystem improvers that have been put in to ensure that the memory operations are well tuned for the LPDDR5 subsystem, which is common in our APUs. So overall, really a larger engine, but improvements in performance per watt and performance per bit to ensure that it fits in the envelope of what we need from a mobile SoC. Taking a quick look at the XDNA engine, there's a third compute pillar along with our CPU and GPU. This engine is best described as a tile data flow architecture with programmable interconnects and a flexible spatial reconfigurability, right? So with software managed memory, there are no cache misses, so you get predictable, dependable performance. With a reconfigurable memory interconnect, you're able to take advantage of the memory bandwidth better, do better resource isolation as well. And with the spatial reconfigurability, it is better suited for the multitasking use cases and the multiple concurrent use cases that are going to show up as the new use cases develop. So overall, generationally, going from Phoenix to Strix Point, we go from 20 tiles of AIE 4 to 32 tiles in a 4x8 array, with each tile capable of 2x the max, 1.6x the memory bandwidth, and improved frequency and voltage tuning. This engine delivers 50 TOPS of peak intake performance. Additionally, we have 2x the number of partitions compared to the prior generation. We had 4 partitions previously, we have 8 now, so even more concurrent applications can be handled while taking care of the real-time constraints that arise out of it. And finally, column-based power gating to ensure that if only a subset of this engine is being employed, the remaining engine can be power gated to conserve power. So going back to what Victor said in his keynote, data types are key to advancing AI, and XDNA2 does its part by supporting block float 16, and that delivers 8-bit throughput, but with 16-bit accuracy. And now this engine delivers, again, a peak 50 TOPS of FP16, block float 16 performance, which again positions it as the most powerful NPU for the next gen AI PCs. So that concludes the Strix point summary of where there have been significant improvements in both CPU, GPU, and NPU, making it the ideal next generation AI PC. Taking a quick look at the Granite Ridge SoC, we did go over those two CCDs that are connected to the I/O die through a die-to-die interface. Again, a maximum of 16 cores, 32 threads, and a 64 MB L3. It's connected to the I/O die through a 32 bytes per cycle data port. Now, the write data path is 16 bytes per cycle. Again, given that the die-to-die interface involves a SerDes and a PHY and operation, it is important that we pay attention to energy. And where we were not getting significant improvement in performance, i.e., halving the write data path, we jumped at that opportunity to make sure that we do design the interface in a way where we get maximum return for the power invested. The main challenge for this SoC from a design standpoint was the fact that we stayed with the N4P technology, which meant that all the IPC that Brad was putting into the Zen 5 core resulted in a larger CCD, and it was imperative for us to be able to support this SoC in the AM5 platform infrastructure. So there were some packaging innovations that had to be done to ensure that this larger CCD can still fit in. Then again, this would be the second SoC that we would support in the AM5 infrastructure. Actually, the last 5 desktop SoCs have all fit in a 40 by 40 package, which I think is an incredible achievement by the design teams and the packaging team. So outside of that, there's no major changes to the I/O die. It's unchanged from the prior generation with some minor changes in the rest of chip to manage power for both active and idle scenarios. So summarizing, Zen 5, again, is an on-cadence delivery of your CPU core with significant improvement in performance with AVX 512 and the 512-bit data path, significantly higher throughput, as well as AI uplift. And with the two design points of the Zen 5 Classic and the Zen 5 Compact, enabling us to deliver truly varied and differentiated CCXs to meet the needs of our entire product stack. The two products we introduced that are anchored by the Zen 5 CPUs, Granite Ridge and Strix Point. Granite Ridge, again, delivers a generational uplift in productivity and creator-style workloads, along with AI, as well as gaming performance, while still, most importantly, fitting inside that AM5 platform infrastructure, which is key for our customers. And when it comes to Strix Point, it's just a no-compromise AI PC solution with significantly improved CPU, GPU, and NPU compute. Really makes it the best-in-class ultra-mobile PC in the market right now. So these designs would not be possible without the tireless efforts of thousands of engineers who have made this happen. So and who Brad and I are honored to represent. So I'd like to conclude by extending my heartfelt gratitude to the engineering teams at AMD who have made this happen. So thank you.
Thank you, Mahesh. Thank you, Mahesh. So we are almost running out of time. So let's open the floor for question. One question from Slack and one question from the floor.
Actually, I was going to say there's a large number of complex questions in Slack. So if the authors could maybe just address them there, and we'll go to the floor.
Sounds good. Okay.
Go ahead.
George Kozma from Chips and Cheese. I noticed that the retired queue, so the ROB, is statically partitioned. Why wasn't it watermarked? And if could it be watermarked? In like, is it possible to watermark? If not necessarily, are you going to?
Yeah, I suppose you could. It's a design choice that we made. We statically partition it. It does simplify a lot of our work. So for that one, we enjoy good performance with it as it is. we do go through, studying the various queues, and that one was less impacted.
Thank you.
So a lot of neat logic was put in, your back end, your front end. You doubled a lot of the logic in the core itself. And notably to my eyes, on the die shot, the L3 density really increased in the new generation. So I wanted to ask if you could speak to anything that changed in the subarray design or the porting of the macros, maybe like prior, Zen 4 dense to allow that expenditure on the logic side.
Yeah, I guess I can say that, we continually look for ways to improve our memory densities, and we did make use of some more dense arrays in the core itself. There was there as well as in the L2 and L3.
Okay, so let's conclude this session. Thank you.
Well, thank you. And again, I like what Mahesh said. Thank you to the Zen 5 team. It was great to be able to represent you.
Okay, thank you. Thank you, guys. So we have a very last talk from Preferred Networks, MN Core 2, and the speaker is Jun Makino. Jun Makino received a PhD from University of Tokyo. After he received the PhD, he worked at University of Tokyo, the National Astronomical Observatory of Japan, Tokyo Institute of Technology. Since 2016, he works at Kobe University. From 2023, he also works at Preferred Networks as the VP CTO of Computer Architecture. His research interests are stellar dynamics, large-scale scientific simulation, and high-performance computing. Let's welcome Jun.
Okay, I'm Jun Makino from Preferred Networks, and today I'll talk about our second generation processor for the deep learning and general purpose application, MN Core 2. So let me start with a summary of the talk. MN Core is a series of the AI-oriented accelerator developed in our company, Preferred Networks. And the first generation MN Core was completed in 2020 and achieved pretty high performance, both for the AI-oriented workload and also the general purpose applications. And we actually received 3 times the number 1 rank in the Green 500 list, if I remember correctly, June 2020, and twice in the 21. And we now completed MN Core 2, and it basically follows the architecture of the MN Core, but we tried to reduce the production cost while keeping essentially the same similar high performance and high performance per watt, and we try to so basically we try to improve the performance per silicon area. So the actual performance or efficiency on the real applications, both for AI and the general HPC application, turned out to be pretty high. And I will actually show the number in the talk. And we have already started the development of the next generation processors, and now both for the training and the inference. So my talk will be roughly organized as follows. Well, I'll start with who are we. We have in this 3 days conference, including the tutorial, we have heard of the pretty large number of talks on the AI accelerators, and most of them are pretty famous companies like Microsoft and Meta and so forth. So we are sort of the last one with coming from the small country and with a name which most of the people are unheard of. So I'll show the brief introduction of our company, and then MN Core and MN Core 2, and I'll briefly show the actual performance MN Core 2, and I'll go to some of the details of the architecture of AmpereOne 2 and how we can write the software for AmpereOne 2 and the future direction. So let me start with so who are we? And the Preferred Networks is actually not the hardware company, but the software company for the application of the deep learning for the workload in mostly in the industry domains. So we are working with companies like Toyota and Fanuc and quite a few other Tier 1 and Japanese companies for the application of the AI to their own area. So our application covers from things like the transportation and the manufacturing and the medical or life sciences and material science and robotics and entertainment. And our company founded 10 years ago, and our office is located in a very central area of Tokyo. You can reach our office from something like 5 minutes walk from Tokyo Station. And we have now roughly 350 employees, and almost roughly 90% of them are working on the software. And our effort to develop the hardware is a pretty small effort with something like 20 or 30 people working on. Okay, so let me start with the overview of our AmpereOne architecture or our development. So the AmpereOne is designed for the efficient execution of the deep learning training, and also and of course this includes the backpropagation. And the architecture is actually quite different from the other AI accelerators given yesterday and today. Our AmpereOne architecture is a very large-scale similar processor in which all of the processing elements in a single package. You can see that in the photo that there are the four dies in the package, and all of the PEs in the single package actually operates in the similar fashion. And the peak performance is 32.8 teraflops for the double precision, and we support the double precision and the single precision and half precision so far on up to AmpereOne 2. And the performance is of the single precision is 4 times higher than that for the double precision, and for the half precision it's 16 times higher. And the power consumption of the first generation AmpereOne is roughly 500 watts, which means that the efficiency performance per watt is something like 65 joules per watt. And there are actually quite a few unique architecture characteristics like that we don't have any cache, and instead we have the on-chip network with a tree topology. Not almost every other processor has the mesh topology, but we have the tree topology which support the broadcast and reduction operations on each level of the network. And these actually are designed for the efficient and easy parallelization of the tensor-oriented operations, which is essential for the deep learning. And we started the development of AmpereOne in 2017, and the first generation has completed in 2020, and the second generation 2023. And we actually started the development of the two different successors of AmpereOne 2. The first one is for the learning, and the second one is for the LLM inference, and I will go back to some of the details of them after in the later part of my talk. So for the AmpereOne 1, sort of the major achievement was one of the major achievements is that it is listed in the Green 500 list 3 times in 2 years. So yeah, so numbers are initially something like 20 gigaflops per watt, and finally something like 40 gigaflops per watt. And this means that there has been quite an effort in improving the performance and efficiency of the HPL implementation. But there has been also the similar improvement in the competitor, which was NVIDIA A100, and that is why we were not listed number one in 2020 November, whereas the A100 achieved slightly higher number. Well, anyway, so now I would like to go to details of the MNM Core 2. The difference, the primary difference between the MNM Core 1 and MNM Core 2 is in the die size. You can see that the MNM Core 1 has 4 fairly big dies. Of course, designed in the SMC N12 technology, which is essentially the 16 N16 technology slightly shrinked, and the MNM Core 2 actually used the N7. So even so, basically we have shrink the die size by roughly factor 5, and still keep the almost the same performance. So this means that the production cost of the MNM Core 2 is much lower compared to MNM Core, the first generation MNM Core. If we compare the performance numbers and the die size with the other GPU or basically GPU, we can see that the performance per die size for the technology similar to N5 and which of course includes N6 is significantly higher compared to the other to the GPU from other companies. And for the actual performance on the real applications, I have here shown the one deep learning application which we are actually using internally, and the sort of the benchmark definitely 50 performance. And for them, the performance is similar or higher, or in some cases significantly higher compared to what you can achieve with A100. And for the general purpose HPC applications, here what we show is more one is essentially the benchmark. Here the benchmark is sort of the famous, well, at least in the HPC industry, the famous benchmark which mimic the rather simple Poisson solver with a 19-point potential in the 3D space. And we could achieve the very high performance on the Himeno benchmark. And of course, actually, this is achieved by having all the data set for the Himeno benchmark on the on-chip memory of the MNM Core 2, which has a capacity of 256 megabytes, and which was impossible with A100. And for the OpenFDT, which is the implementation of the FDT method for the electromagnetic field simulation, the performance is also higher compared to the A100. Now, let me go into the architecture. In the top level, the overall architecture is sort of similar to any other GPUs in the sense that we have in the lowest level what we call the processing element, and which is very close to the single CUDA cores, and we have the MAU. MAU is the I don't have the information in the slide. MAU is a matrix arithmetic block, which is essentially corresponding to the tensor core of the NVIDIA GPUs, and we have the cluster of these tensor core and CUDA cores to form the L1B, which is essentially the streaming unit of the CUDA. And for the higher level network, we have another layer of the tree structure, which we call L2B, and in the entire chip consists of the 8 these L2Bs. So in total, we have the 4,000 processing element or 1,000 matrix arithmetic blocks. And we have for the external memory, we have the GDR6. The GDR6 interface, I believe. And so the overall architecture, sort of the difference from the other architecture like the NVIDIA GPU, that this entire chip actually operates on the single instruction stream. And this is very similar to the architecture of the large-scale simulated machines in the 90s, like the thinking machines HC2024 or mass prime MP2, and of course, as I hope that everybody here knows, the mass prime the software and hardware of the mass prime MP2 is essentially the successor of the CUDA software. Well, anyway, and the main difference from the large-scale simulated processors in the 90s is that the network architecture is simplified and also optimized for the deep learning with the explicit support for the broadcast and reduction. Well, let me now go into the very detail of the PE architecture. Here, what I show is the structure of the processing element. And you can see that there are multiple GRFs, general purpose register files, and the multiple local memories, and one what we call the T register, which is oxygen register, which is very similar to the S registers of the Cray one. And the sort of the unusual architecture here is that these defined memory units are all visible from the software, and the local memories can supply the operand to the matrix arithmetic unit and can receive the result directly from the arithmetic unit, and the matrix arithmetic unit and the integer AL can operate in parallel. So we have the very long instruction architecture, which can specify the operation of every single element of the PE explicitly. So the instruction word length is, if I remember correctly, something like 240 bits. And so the compiler and the compiler needs to assign the variables to the appropriate register or memory unit, so that it can prevent the hazard. And the level 1 and the level 2 networks are pretty simple. We have for the level 1 network 16 of these matrix arithmetic block, which consist of the PE, 4 PEs and the matrix arithmetic unit. And the one L1B consists of one shared memory and the 16 MMBs. And here, as I said already, there's broadcast and reduction networks. So L1B can broadcast the data to all MMBs and can take the summation. And these are the two most important communication patterns for the processing element used for the tensor operation in the deep learning. So we have the hardware support for these operations, which actually are quite important in the reducing the hardware complexity and the power consumption. So these are against the comparison between the ML core and ML core 2. The only important difference is that the number of L2Bs is reduced to to 8 from 16, and the clock frequency is increased by factor 1.5. And the other things, well, there are many small changes, but I can skip it here. For the software, I just say briefly go through the compiler for the deep learning. Basically, we start from the anything like the PyTorch or Onyx model, a network model, and that one is from the several stages of the compiler layers becomes the actual assembly language code or machine code for ML Core or ML Core 2. And since we don't have the cache, we for each of the metrics or internal I mean the intermediate metrics or tensor, the compiler needed to find out the way it distributes them to the PE, or also the user can specify that way, and which is passed to the global layered planner in the first level. And so these are all done in the software, and so if everything works fine, the change in the software you need to move from the use the PyTorch code on GPU to the PyTorch code for the ML Core is pretty simple. You can just replace the backend and the name of the trainer and that's all, and the description of the model is essentially the same. Okay, so now we started to provide as a commercial product ML Core 2 as of last week. So if you are interested in buying one, you can find the contact point there. Okay, and so for the architecture summary, it's something like this. Matrix vector unit is available on each PE, and then we have the single precision, half precision and single precision and double precision. And the logic circuit is actually shared for these different word lengths. And we have the register memory architecture and the hierarchical on-chip network. And these actually help us to achieve the very high performance per watt and very high performance per die area, and yet the high application efficiency. And of course, this one needs very unusual compiler, which was not made anywhere previously. And so it took some time to develop such compiler. And for the next generation, we have started the development of the next generation for learning. We have added the budget from MIT, and this will be made with Samsung SF2 process. And also we started the ML Core next for the LM inference. As we heard many times today, the LM inference performance is limited by the memory bandwidth. So for this one, we try to improve the memory bandwidth using somewhat exotic technology, and we hope to improve the inference performance for factor 20 from the current generation in Core 2. Okay, so this is the summary of the talk, which is the same as what I gave in the beginning of the talk. So I guess I can that's all, and it's now this is time for Q&A. Okay.
Thank you, Jane, for the presentation. Let's start from the question on the Slack channel.
Okay, these questions are mostly targeted towards understanding what the use case is for the product. The Green 500 results, the SIMD architecture style, the high precision, double precision in particular, suggest that your target is more for supercomputing and HPC. But you did talk about deep learning in your slides, and you suggest that machine learning is a target. Mm-hmm. So do you have any performance on machine learning applications that you could talk about?
Well, here, in the slide. And so in the slide 9, we have the performance comparison for the deep learning application, like the typical less than 50 performance.
Okay, so primarily these applications are the ones that you focused on.
Yeah.
Okay, thank you.
Okay, more questions from Slack? Go ahead.
In the P core slide, you show an IALU. I assume it's an integer ALU. Is that a scalar unit? Will process.
Can you please repeat your question? Go forward too.
So on the slide for the processing element, the PE, you showed an IALU. I assume that's an integer ALU. Does that process one 64-bit operation per cycle?
This one, yes. This one, well, actually, one 64-bit element, or what to started to so this one also has the similar feature like the one double operation or two single operation or four operation numbers.
Okay.
Go ahead.
Okay, I'm going to come back around to your high precision, your double precision floating point. There's extra power for supporting that particular number format, and you look like you're aiming for low power. So can those units be reused for lower precision if that's suitable for the application in order to reduce the power? Sorry, you've got double precision functional units. Can you reuse that hardware to do lower precision so that you would be using less power for the computation if the number format was appropriate for the application?
Well, actually, our matrix arithmetic unit are designed that way. So the multiplier unit is actually the same. Multiplier unit is used for the AP16 and 32 and 64 units.
Okay, so you can basically use that hardware in a more power efficient manner if the data size is smaller.
Yeah.
Okay, thank you.
Okay, thank you, Jane, for a nice presentation. Thank you very much. Okay, this is the end of the last session.